Welcome to our presentation Generating Android Tests using Novelty Search. Let's briefly motivate why Android test generation can benefit from Novelty Search. Consider the following example. On the left we have some kind of registration activity that requires specific inputs, the selection of a date, and at least checking the terms and conditions checkbox and then clicking the submit button to eventually reach the target activity. Let's further assume that we use some classical fitness function that relies upon a distance metric. However, this kind of fitness function can give us only some limited guidance, since it does not know which specific inputs are required to reach the target activity. To overcome this problem, we can make use of Novelty Search. We can reformulate the previous problem through the given maze. Here the objective is to find a path from the start location to the finish point. With a distance-based fitness function, we likely observe the following situation. The search promotes solutions that are described by the green arrow. However, in this situation, we get very close to the finish location but get stuck because the search cannot observe that there is an obstacle and we need to find a different path through the maze. In contrast, with a novelty function in place, we likely observe the following picture. We may start with a similar path, but since a novelty function does not promote solutions based on its distance to the finish location, but rather on its novelty, we may end up with a path from the start to the finish location. The first novelty function we propose is based on a k-nearest-neighbor based approach, where a new solution, here highlighted in red, is compared to the k-closest solutions, which can be 3, 5, 7 or whatever. The chromosome is more novel the higher the distance is. Typically in such a KNN based novelty function, the most novel chromosomes are also stored in an archive. And novelty search approach is based on subjective logic. To get an idea how this works, we start with a subjective opinion state machine, shortly called SOSM, that is shown in the given picture. The state machine illustrates a file editing application where we start in state A and can open a document to land in state C. Then we can edit this document to land in state D, edit it several times, stay in state D until we either save the changes and land back in state C or close without saving the document. And eventually we exit the application and land in state B. The first task we will perform is to assign the observed frequencies in terms of absolute numbers. For instance, the open transition is triggered 6 times, while the save transition is only observed 3 times in our example. Step is to map those absolute numbers to relative frequencies as shown in red. Form, the shown finite state machine represents essentially a probabilistic state machine, where one could compute the probability for reaching some specific state by multiplying the transition probabilities alongside that path. However, if the number of observations is very low, the computed probabilities might be misleading. To compensate this, a subjective finite state machine computes a second order uncertainty that describes how much confidence we have in the given probability. To compute a subjective opinion for each state and transition, which is composed of an uncertainty value as well as belief and a priori mass, we need to fill out the following table. The first step is to fix a parameter called alpha that describes when we consider a probability as certain. Here we assume that we need to have at least 20 observations for a specific transition to consider it as certain. We can start computing the a priori distribution. We initially assume that each transition or event is evenly likely. That means when we have 5 events, the a priori probability is 0.2 for each event. Next step is to compute the uncertainty for each state by following the given formula. We sum together the individual frequencies per state and divide by the predefined value of alpha, which is in our example 20, and then we subtract it from 1. When we substitute the variables in the formula by the concrete numbers, we end up with an uncertainty for the state A of 0.4. Now we can compute the belief mass for the state A, which is 1 minus the uncertainty of state A, which equals 0.6. We can distribute the belief mass to the individual events by considering the frequency. Since there are only 2 events that happens in state A and both have the same frequency, we split up the belief mass of 0.6 in 2 parts and assign to the open and exit event a belief probability of 0.3. Finally, we can perform the same computations for the state C and D. Note that we omitted state B because it has no outgoing transitions and use is irrelevant in our consideration. With this information, we can complete our example by mapping the computed uncertainty and belief values to the individual transitions. The disbelief value is then computed by computing 1 minus uncertainty minus belief. That means uncertainty plus belief plus disbelief must always sum up to 1. Now we can compute a subjective opinion for a specific path. By using a specific multiplication operator that multiplies the individual uncertainties, belief and disbelief probabilities. With the help of such a subjective opinion state machine, we can compute the novelty of a particular solution by taking the uncertainty and adding it with the disbelief multiplied by some disbelief weight that controls how much emphasis is put on the disbelief. Since other research in the novelty search domain has shown that it can be beneficial to include coverage, we slightly adjusted our novelty function to incorporate this metric. That means the final novelty is computed by taking the novelty according to the uncertainty and disbelief values multiplied by some novelty weight factor and summed up with the coverage value. Now, how does novelty search work in Android? Assume that we have a chromosome that consists of several actions, for instance, click action on a specific button, swipe operation, filling out a form, followed by some additional actions, and ending with a back action. We can now execute this chromosome in an emulator and get some traces, which describes, in our case, the visited lines of the application under test. Now we can repeat this process for an entire population consisting of n chromosomes. Depending on the chosen novelty search algorithm, we have to either update the archive, which is the case in the KNN based novelty search, or update our SOSN model when using the SOSN based novelty search. This brings us already to the evaluation part for our study. We investigated how the novelty search algorithms, so both variants, compare to random exploration and state-of-the-art search-based approach mu in terms of coverage and the number of unique crashes. The entire approach was implemented in the Android test generator called Mate, which is under active development and can be found on GitHub. Feel free to check it out. Before we actually compared the performance of our novelty search algorithms, we performed some parameter tuning on both novelty search variants. We used therefore 10 apps, which we repeated 10 times to compensate randomness, and each run took 1 hour. For the KNN based novelty search variant, we studied 6 different configurations where we adjusted the k nearest neighbors parameter called k and the archive size limit. For the SOSN based novelty search variant, we investigated 18 different configurations by adjusting the certainty threshold parameter called C, the disbelief weight called D, and the novelty weight The results for the KNN-based novelty search approach are shown in the given table. For each configuration, we compute the activity and lane coverage and the number of unique crashes. Based on these numbers, we can compute a tournament ranking score, which is computed as follows. We took pairwise two distinct configurations and checked whether there is a statistical significance at a p-value of 0.05, and only if there is such a significance, we use the Wager-Delaney effect size to increase the tournament ranking score for the better configuration. The configuration with the highest tournament ranking score is deemed to be the best configuration, which is for the KNN-based novelty search the variant using a value of K5 and an archive size limit of 5 as well. The same procedure was repeated for the 18 different configurations of the SOSM-based novelty search. And here the last configuration in the table is the best configuration. The experiment for our research question looked as follows. We took 108 complex apps, where complex refers to applications that have more than 5 activities. We repeated each execution 10 times for 1 hour. The coverage results are illustrated by the two bar charts. We can observe in both cases the same order. The leftmost column refers to MIO, followed by the KNN-based novelty search and the SOSM-based novelty search, and on the right side the random configuration. You can observe that MIO is slightly better than both novelty search variants, and both novelty search variants are somewhat better than random search. While we get a similar picture for the unique crashes. Here, MIO is also the best configuration, followed by the KNN-based novelty search and the SOSM-based novelty search, and at the last place the random exploration follows. Overall, we can say that the novelty search variants are better than random exploration, but can not yet compete with MIO. We believe that we need to improve the underlying genetic algorithm and sample, for instance, new solutions based on the SOSM model, or randomly like MIO does. This brings us to the conclusions of our presentation. We have seen that the genetic algorithm using a classical fitness function can get stuck under certain circumstances, whereas a novelty function based on either a k-nearest neighbor based approach or on a SOSM model can overcome this problem. The evaluation has shown that the proposed novelty search variants can outperform random exploration, but can not yet compete with MIO Thanks for your attention.